The topic in your book is called Fluids in Motion. I just call it Fluid Flow. Okay, which is a huge topic. Again, it's all these things we talk about, very, very widely used. So, the most, or somebody else tell me, give me a basic example of something that where there's fluids flowing. Very, very simple example. A river, there's one. The thing inside of it? Okay, I can think of that. It's not flowing, but I understand you're saying things are flowing past it. Good idea. What else? What are some other examples? She said river, Mark? Water from a faucet. Like water's inside of pipes. There are so many laws that we use to govern pipe flow and water flow in pipes, it's unbelievable. If you have, for example, imagine you have a pipe that runs like this. Okay, normal pipe. Then suddenly, the cross-section of the pipe becomes much larger. Something else happens there. It's a big thing that happens there. We're going to talk about that today. What happens to the fluid flow, the velocity, whether it's turbulent versus laminar. We'll talk about those words. Or what about this? What if you have a pipe that goes around what's called a bend or a corner? There's a big thing that happens there, actually. We have to talk about that, too. If you have a pipe that actually is like this, it's different than this. Those are different pipes. Every single time you have a different shape, a different law is used or a different property is used. We're going to use Bernoulli's laws, which is the general guy, Joseph Bernoulli and Johann Bernoulli. Which some of you might remember, 10th grade, I had you guys do projects on mathematicians and scientists, and Bernoulli was one of them that we worked on in 10th grade. All of his laws mainly governed fluid flow. And Pascal's laws were about fluids in containers that were controlled with the pressure. So what we're going to talk about today is how does fluid change depending on what shape it's going through, or depending on the type of flow, or how much flow there is. Or for example, like, you ever gone whitewater rafting or heard of it before?
Yeah.
Like, what is whitewater rafting actually? What is
It's
it?
scary. When you
It's
put a
scary.
little thingy in the thingy-majigger and you go like real fast.
Okay, you go real fast. Why is it called whitewater?
Because it's like
The
water gets white.
The water looks white from all the turbulence, right? The water is constantly churning in whitewater rafting. You're hitting lots of rocks along the way. There's like, there's cliffs along the way that you drop off a little bit, then you go to the next level. All this turbulence of the water causes that like foamy look. That's why it's called whitewater rafting. Okay, that's why it's called whitewater. Now, you have levels of whitewater rafting, obviously. Ever been in an airplane and the guy comes on the speaker, the pilot maybe, and says, "We apologize, we're experiencing some turbulence at the time." And you sit back and buckle up. And you wonder, well, what is this turbulence, right? Things are shaking. Well, why is it? Turbulence simply means that the flow of the air around the airplane is not laminar or not smooth. Not smooth. It's like if you have this flow that's causing it to shake because in the back of the plane, so in the front of the plane you have this nice flow, and then you have this turbulent region behind the plane which is causing it to shake. That's what's causing it. Same thing with water. If I took, my water bottle and simply just poured it lightly, that would be laminar flow. Okay, then if I poured it and I took the whole thing and just dumped it out and it just splashed everywhere, that's an example of turbulent flow. Now, there's something we're going to talk about called a Reynolds number. And it's only called a Reynolds number because of the person that invented this. And if you exceed the Reynolds number, you're considered to be turbulent flow. And you can measure this number. It's not just velocity. It's not just how fast it goes. That's velocity. It's not the cross-section itself. It's not the amount of water, the mass of water. There are a lot of things that go into it which determine what's called a Reynolds number. If the Reynolds number is below a certain level, it's called laminar, meaning very constant, nice, easy, predictable flow. Turbulent is like unpredictable, like irrational, like pi. You don't know what's going to happen with the turbulent flow. Could we go whitewater rafting? I've done it, but could we go? I'd probably say no, because it's really dangerous, especially, like whitewater rafting level 1 or 2 is nothing, That's like downstream. But if you want to really go whitewater rafting, it is pretty dangerous. You should take lessons and stuff.
Well, not like the extreme, advanced.
Well, we're working on Six Flags right now. Let's get that first. Okay. I love rafting, though. It's a lot of fun. So the idea today is about fluid flow. We're going to look at some basic laws, okay, very simple ones. We're going to look at something a little bit more complicated than the idea between turbulent versus laminar. Okay, so that's our goal today, to go ahead and look and see what the difference is between these types of flow. So let's start. Let's start by drawing a cross-section of a pipe. Imagine the pipe starts like this. Okay, then the pipe bends around, but it opens with a much wider opening than it started with. So again, for example, we have a pipe flow where there's some water coming in here, or some fluid, in this case, it could be anything. And then the fluid travels through the pipe, and it comes out the other end. And the other end on this end happens to be a bigger cross-sectional area. Who can tell me from their own experience? You got in the backyard, and you have like your garden hose, you go to, say your parents or somebody's guarding the hose in the backyard. If you put your finger over the end of it, what happens? It starts shooting everywhere, doesn't it? Like if you put it in the wrong spot, it'll just go anywhere. If you put your finger over, like, say half of it, it shoots off like a faster stream, right? What are you doing when you're putting your finger over it?
Pressure. Yeah.
Believe it or not, guys, don't use the word pressure. And here's the reason why. That's one of the other misconceptions. Pressure is actually less when you put your finger over it. It's not more pressure. What you're doing is you're lowering the cross-sectional area. And I'll explain in a minute where that comes from. But it's your cross-sectional area that it comes out of. So for example, look at the vent up top. If we had, for example, instead of all those slits, if it was just an opening, if that was just one big opening there, the fluid flow, or the air, would be coming out at a slower rate. When you lower the cross-sectional area, you actually increase the velocity of the fluid, or the rate at which it comes out of the opening. So the way to prove this is actually pretty simple. Think about it logically for now. You have a certain amount of water. Let's say a certain amount of water is coming in here. And I look at this instantaneous point in time. Right here, there's a certain amount of water right in there, right? Now, that same amount of water is traveling through this pipe. And when that water gets up here, it looks like that really now. Again, there's all this water backed up here. But when it gets up here, it's got a lot more area to come out of. So that same amount of water, this one piece of water, and I know you can't really do this, but you have to visualize. But this one piece of water here is now kind of like spread out across the end here. Okay? And what you want to say to yourself is this. The same amount of water that goes into the hose from the sewer system comes out of the hose. And think logically. It's just about conservation of mass. If I put so much water into the super soaker, and I have a gun, and I shoot the water out, in the end, how much water is going to come out? All the water that you put in. Obviously, there's evaporation and stuff, but generally speaking, the amount that goes in is what comes out. So the mass of the water here is the same as the mass of the water there. Again, you have the same amount of water. Well, amount of water is the mass of the water. The amount of matter is mass. We're not even looking at volume now, we're just looking at mass. So we can start by saying the amount of water going in is equal to the amount of water coming out. So we have those two things to start. Next, once the amount of water is going in the same as going out, we have to then say to ourselves, how do we represent the mass? Leave it over here. How do we represent the mass? We said just rho v. So call this rho 1 v1 equals rho 2 v2. Okay, where rho is what again?
Density.
Density. And then v is? Volume, not velocity. Be careful, people. When you replace mass with rho times v, that v is volume. That's why we have rho vg in one of our formulas for pressure. Okay, rho vg. Now, with those two things said, we want to then compare and say to ourselves, well, what can we do about volume? This is where it gets a little bit tricky. The volume, and this is where you have to start thinking about prisms, and we talked about this last week. Imagine these are pipes. What shape are pipes really?
Rectangle.
Cylindrical or circular cross-section. They can be rectangular. If you look at the ductwork in a building, and you look at the HVAC system, the heating, ventilating, air conditioning, if you look at the system in the ceiling, you'll see that some of the ducts have rectangular or square cross-sections, whereas some of the pipes in the building have circular cross-sections. It doesn't matter which one it is. Either one works here in this application. But I'm imagining that this is water flowing through a pipe. And whenever there's water flowing through a pipe, it's a cylindrical cross-section. Okay, it's not going to be rectangular. Airflow in an HVAC system is a lot of the time rectangular because it's easier to manufacture. That's the real reason they're going for that. Okay, but let's say we have a cylinder here. If I want to know what the volume of a cylinder is, and let's say I happen to know the area of the base, and I want to know the volume of that cylinder, how can I figure out the volume of the cylinder if I know the area of the base? Times the height. Again, volume is always area of the base times the height. Whenever it's a prism, it's the example of the coasters. Take a coaster. We all know what a coaster is. You put your drink on a coaster so you don't get the ring on the table. Take coasters and stack them up. Eventually, don't you get a cylinder? You're taking the area of that one coaster, and to get the volume, you're multiplying by that height. That's the extrusion process we talked about. So here, what I want you to think about is this. This is really three-dimensional. This is really three-dimensional here. There's a third dimension into the board. This is really like a circle at the opening at the end there. And this end is really another circle that's at an opening. So the area of that base is just simply a circle. Well, what I can call this, if we think about the kinematics, this is like delta x. That's how far the water goes from beginning to end. The water might start here, and then this much water travel to here. Then the water flows all the way through, it gets to here, and it travels over here. Well, take a look at the delta x's. Don't they look very different to you? Which one is bigger? Would you say delta x1 or delta x2? Delta x1 is clearly longer. Look how far delta x1 is, and look how far delta x2 is. But if I think about this now, and I take my head and just turn my head like this now, it's just a cylinder. Again, the area of the base is whatever the area of the opening is, times the height of the cylinder. Well, the height is delta x1. Turn your head over here. This is the area of the base, is the area of a circle, times the height of the cylinder, delta x2. So what I'm going to do is this. I'm going to rewrite this as, oops, I'm going to put a delta. On the left side, again, my volume of this mass here, the volume of this first region, is like the area of the opening, A1, times the height, delta x1. Okay, we're doing a derivation right now, obviously. Okay, we'll come up with the exact formula. Here we're going to have rho 2, A2, delta x2. Now, at this point in time, we have to discuss several things. First, how can you define delta x in terms of velocity? Think back to chapter 1 in kinematics. If I had a delta x, or a change in displacement, how can I relate that to my velocity? What was my formula that I always remember to relate velocity and displacement? Good, displacement over time, or distance over time. So we know from chapter 1, let's write a little side note, velocity equals your displacement, delta x, over your time. I put v bar, it doesn't have to be v bar, let's call it v for now. So velocity is delta x over t. Is that clear? Yeah. Again, this is from chapter 1. Solve for delta x. When you solve for delta x, what do you get? Good. Vt equals delta x. Just take the t, and move it on up, like we always talk about. So replace your delta x now with Vt, but with the correct subscripts. So rho 1, A1, V1, T1, rho 2, A2, V2, T2. Okay. Now, let's go ahead, and this is the part that's a little bit trickier, and I'm trying to come up with an easiest way to make this make sense. First, the fluid that went into the pipe, isn't it the same as the fluid that comes out? Yes. So what do you know about the density of those fluids? They're the same. So does the rho 1 and rho 2 have any effect on the problem? Because they're the same, aren't they? So what can I do to them? Yeah. Okay, start with that. Again, the density of water coming into a pipe is the same as the density of water coming out of a pipe. It hasn't changed. Okay, obviously we could say that, yeah, sure, maybe like copper came off the wall and it got a little bit, got a little bit polluted in a sense, and then you could really say the density changed, but theoretically it's the same fluid going in and out. Next, the tricky part is this. Since we have two different cross-sectional areas, most people think it takes different time. The time it takes for this fluid flow is identical. So with that said, what we can say is that T1 is equal to T2 here. Again, the time it takes, and this is the hard part, and think about a hose. The water coming out of the end of the hose when you're watering. If you put your finger over it, the same amount of water is still going to come out, it's just coming out faster, right? It hasn't really slowed down the water, actually. Because the water coming out of the pipe system is so strong that it's not, you putting your hand over it is not going to work. Try it sometime. Try and stop the flow of water coming out of a hose. It's not going to work for you, right? If you put a cap on the end of it, with like a nozzle, and then you close the nozzle, sure, it'll stop it. But if you just try to put your hand over the end of it, it's not going to work too well. The water's going to start shooting everywhere. The flow of the water is going to continue to be the same. So the delta T, or the time it takes for the water to come in this part and the water coming out, is the same. It's the same amount of fluid going each way. So T's actually end up dropping off also. So what we need to remember for this is simply A1 V1 equals A2 V2. Okay, and this is one of our continuity equations. And unfortunately, this topic is very, very widely used, but only widely used after you learn like 2-3 levels of calculus. All the equations that come about, that come from where a lot of these formulas end up coming from, are all derived from different levels of calc. And I encourage you guys to do that and look at it, but I'm not going to go through the derivation today because it wouldn't even make sense. Even if you're in calculus now, it's not going to make much sense to go through it. Okay, because it's material that we haven't gone through yet. But again, when we talk about physics, we're trying to model things right now. So we're simplifying. We're using this model. So let's now look at this equation here. Okay, I have an area coming in, right? And the area coming in, was it bigger or smaller than the area coming out?
Smaller.
It was smaller, wasn't it? So Elizabeth, give me a number for this area. Any number. 2. Mark, if this is 2, if the area here is 2 and we said this is bigger, give me a number over here. 7. All right, so let's do that. Let's go ahead, put a 2 in for this area and a 7 in for this area. I don't care about units right now, hypothetically speaking. James, take a number from 1 to 10 and we'll make that the velocity for the inlet. 4. So the velocity coming in is 4. All right, so now let's figure this out. If the velocity coming in is 4 and its area is 2, but then my area went up, what's 2 times 4?
8.
And this has to be 8, doesn't it?
Yeah.
So this is going to be a number like 1 point something.
Yeah.
Okay, it's really 1 and 1/7.
Yeah.
Okay, 1 and 1/7 would be your actual value there. But look at the velocity change. Your cross-sectional area went up a lot, and your velocity, it went down a lot. Just like if you lower the cross-sectional area with your thumb, what happens to the velocity? It shoots up. So look at the reverse direction. Imagine you have a big cross-sectional area, the normal cross-sectional area of the garden hose. Now the cross-sectional area reduces to 2. Well, the velocity went from 1 and a change all the way up to 4, which is exactly what happens outside. So what can you say about these things? Very good. One more time, Larry.
As the area increases, the velocity.
Very good. So what are they? How are they related?
Indirectly.
Good. Indirectly. Danae.
Read it one more time.
Oh, I just did the math in my head. It's going to be 1 point something. Because if we know that this is equivalent to this over here, okay, then this times this has to be 14. This times this has to be 8. And then 7 times 1 and a 7th actually gives me 8. So this is like 1 point something something. It's just a number. All I'm trying to show you is that the velocity went from a big number to a smaller number. Okay, we could have picked a number like 8 here. It might have made it easier. If I had made this 8, then this would just be simply a 1 here. So that makes it easier for you to make it 8 and 1. But the idea is this. If the area goes up, the velocity goes down. Okay, so let's write that down. As the area increases, the velocity decreases. As the area decreases, the velocity increases. And take a look at the proportion that it goes by. Look at the example now with 8 instead of the 7. Let's make believe we had chose 8. Okay, make believe I chose 8 randomly. So if we had chose 8 here, let's see exactly what would have happened. This would be, that's what we're trying to solve for, right? So our area went from 2 to 8. What did it do? It went up by a factor of 4. It got quadrupled. From 2 to 8 is a factor of 4. This went from 4, and what do we say this would become? 1. This went from 4 to 1. What happened to it? It decreased by 4. So think about it this way. If you're in your backyard, and the water's coming out at a certain velocity, and you want to double the velocity, what do you have to do to the area?
Make it smaller.
Half it, or make it smaller by 2. If you want to triple the velocity, you have to cut the area in 3, or by thirds. So think about if this is the cross section of the hose in your backyard. The hose runs a certain length, and you want to double the velocity. Your thumb needs to cover half of it, so that it's half the area, thus double the velocity. If you want to triple the velocity, your thumb needs to cover 2/3 of it, really. So you need to have your thumb covering pretty much those 2/3 now, so that only 1/3 of it can come out, so that it's triple the velocity. Again, because it's indirectly related. So as you make that area smaller, as you keep covering it up with your thumb, let's say you only leave 1/9 of it open. Well, it's going to come out 9 times faster now, because it's indirectly related.
But then what if the whole area was covered?
Well, that's the thing. If the whole area was covered, two things. First of all, it's not going to work with your hand. But if you put a nozzle on the end of it and then turn the hose on, no water is going to come out because there's no flow rate, and that's different. That's the idea that you have some sort of outside force acting on it. So the stoppage at the end, or the cork at the end, is what stops it. So clearly, if you think about it this way, this is your area of 2, right? If your area here becomes 0, this actually goes to infinity, believe it or not. Because infinity times 0 is what that turns out to be. But you can't have infinite velocity, right? What would that mean? I mean, the velocity would be so great that it wouldn't exist almost. So you don't have that. The velocity actually just stops.
What causes pipes to explode?
What would cause them to explode? Many things. I mean, it depends on the pipe. You could have a weakness in the pipe where there's some corrosion, and over time the wall is getting thinner and thinner, and then eventually there's a lot of flow rate, a lot of pressure built up, and then it will actually cause it to break. There's many things that can. Puncturing. I'll give you an example in a second. Okay, sir.
Because like once you block the roads and whatnot, and you leave the water, should the water just build up and eventually just explode?
Well, here's the thing. In your piping system in your house, you have what's called a ball valve, and the way it works is as follows. There's a valve in there. When you turn on the hose, it actually opens up the valve. Now there's an automatic, and it's called like a backup valve. And if there's enough pressure built up, it automatically chips in, and it turns it off automatically. So even though you have the valve open as if water's coming out, if you can stop the flow at the end of it, it knows, it senses that pressure buildup, and you can actually hear it. Have you ever turned on your faucet and you hear like poop, 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 and then the water starts coming out? You hear that like pressure buildup? Okay, that's the pressure built up in the lines. And then you open it, you're releasing the valve, and the pressure's getting released. If you turn that open, and then somehow you are able to cork off the end of it, it'll actually close the valve. It'll have like it's just a backup valve. That's all it is. It's a safety valve. Okay, it's a safety valve. There's many terms they call them different things. There's ones that are called gate valves. Gate valves are used a lot. A gate valve is really, when you're turning it, that's when you're opening a gate valve. The more you turn it, the more flow comes out, right? Turn the hose a little bit. What happens? Only a little bit of water comes out. There's a gate that's opening. And as that gate opens more and more water is allowed to come through. Okay, it's very intricate. The setup for fluid flow, though, is also a good example in your car. Have you ever tried to start like either a lawnmower or your car and you hear it choking? It's not getting enough oxygen. That's what's happening there. For combustion to occur, it needs enough oxygen. If you don't get enough oxygen or fluid, oxygen is a gas, which is a fluid, you don't actually have enough to start the combustion. Once the combustion process starts, then your engine starts going and it stays going. So sometimes you might have a leak in your oxygen line. So in your car, if you don't have enough oxygen in your intake going in, the car itself won't start. So when you bring it to the dealer, they might say, oh, you know, it's your O2 filter. You can have a filter that filters how much oxygen comes in and out. A lot of it is electrical now. A lot of it, there's sensors, and it can sense it, so it'll shut it off and turn it on respectively. But back in the day, when cars were built without computers in them, how did it work, you know? They had to adjust the valve based on the intake of oxygen so you get enough oxygen for combustion so the car could run. Depends on the scenario, but there's a lot of applications of it. Here's what you need to remember, again, guys. As the cross-section changes, the velocity is always going to change. All right, let's look at an example. Let's look at an example. If the radius of a pipe at the inlet, what's the difference, inlet, outlet, everybody? Inlet, outlet? One's an opening, one's a closing, but is there really any difference here? Okay, just remember, inlet, the water flows in, outlet, the fluid flows out. Use the words obviously, okay? Please don't confuse them. But again, there's no difference really. They're both just openings to the pipe. If the radius of a pipe at the inlet is 5 meters, okay, which is a very big pipe, we're talking about pipes underground. Think about a radius of 5 meters. We're talking about a huge pipe with a lot of fluid flowing through, which is normal. It's 5 meters, and the fluid flow is 20 meters every second. Find the radius needed at the outlet so that the fluid flow there is half the inlet. Okay, is half the inlet. So if the radius of a pipe at an inlet is 5 meters, and the fluid flow is 20 meters per second, be careful, find the radius needed at the outlet so that the fluid flow there is half the inlet. And again, I'm asking the radius, right? I'm not asking for an area. So don't assume that because it's half, it's going to be double kind of thing, because we have a radius now. So let's start. What's our formula going to be to start this?
A1, B1.
Okay. Now, before we can actually do this, we have to think, what does a radius mean? What kind of a pipe do I have? If I have a radius. Circular cross-section, or cylindrical. Very good. It's a cylindrical pipe which has a circular cross-section, simply because we have a radius here. We have a radius. So, start with your thoughts. Say, okay, this is just pi r1 squared v1 equals pi r2 squared v2. Why am I calling it r1 and r2?
Because you got inlet and outlet.
Very good, and they're different, clearly, we said. Find the other radius. But does the pi have any effect? No. Because what happens to the pi? It drops off. So now we have this other formula, r1 squared v1 equals r2 squared v2. That's fine. It's the exact same formula as we had in the beginning, but now instead of area, we're looking at it in terms of a radius. Elizabeth?
What time do we get our?
I have no idea. We're just going to keep going. Okay? I really don't know. Let's just keep going, please.
That was it, and
No, guys, that's definitely not our bell. We were in here for 20 minutes. It can't be. Can it be? Am I losing my mind? Let's hear for an announcement. That's insane if that was our bell. We were not in class 20 minutes. It's supposed to be 15.
They're not following the schedule.
Yeah, it's not on the regular schedule anymore. That's why. I don't know what the schedule is, guys. Let's finish this problem. I'll pull down and check. Okay, you're all going where? Pre-calc or standing calc? So we're not worried right now, okay? Is anyone not going to pre-calc? Where would you be going? Quick.
No, Jim.
Jim?
Pre-calc.
Okay, so we're good. Don't worry. All right. Now, I don't think I can't be over here. We're in 20 minutes.
They're not even using those bells, Mr. Howard. They're using the interphone. Come in.
No.
It's like, come in. All right, it's the big to be found. I only have the word start. I don't have the actual.
Get an autograph?
Yeah.
Oh, wow.
We can take a picture of it.
So what?
I've seen it before. I know, right? Because like you know what's screaming the loudest.
Did you hear?
Did you hear Makita? No.
My vein popped out.
She was only staying on that. Yeah, she wasn't listening. The middle. You want me to go on?
Nobody there. What do you know? It's calling every number.
During the whole thing, people had to call you their phone or when the lady was like, we are telling you something. Nobody else. I was like, yeah, no, I'm telling you.
That's scary. Guys, anyone want to 12 on a Monday? I know that. I agree with you. I'm just wondering if there's some sort of change.
It's 52 minutes supposedly. But
It's not, obviously, now. Okay, thank you guys. We're here for what?
That's what I'm saying. That's not
It's probably not.
Let's keep going.
I think that's the
Clocks, bells, big coffee.
Can you figure out what's good with the bellies? Is that the bell to end the class?
Adolfo.
This is supposed to say yes, I go to my school.
Okay, go guys. Go ahead. Talk to Lauren first.
He didn't do it.
Sorry, I gotta have time to
James like, hey.
Oh, that's okay. Okay, man.
Yeah.